Can everybody see a slide? Anybody can see a slide.
Yep.
Yep.
All right, great.
I can see it.
So far, so good. All right. So kind of met everybody a couple weeks ago when we all started and introduced ourselves. My name's Todd Abhaham. I work here at Iowa State, and I work on an integrated data system that was constructed a couple years ago and is moving forward. So in my work, a lot of, probably about 95% of what I do deals with administrative data records. And so these would be records that have identifiers in them, names, addresses, phone numbers, all that fun sort of stuff. And so that opens up a huge can of fun when every agency in the state deals with data a different way. So I do quite a bit of restructuring. I'll be talking to you tomorrow about data cleaning, which is something I spend a ton of time doing. And then the other big component of what I do as part of our integrated data system is record linkage, connecting data from multiple administrative sources. And so we'll be talking about that a little bit tomorrow too, and it will become obvious why restructuring and cleaning are such an important part of any project. So in terms of restructuring, assuming something moves, there we go. What we're talking about is changes. And so if you consider the original data source, whether it be administrative records, in my case, census data, state data, county data, scrape data, Facebook.
Wow, I think my, oh, sorry. Didn't realize I was on mute.
Did the slide change for everybody?
Yeah.
Great. All right, so talking about making changes. And so once that original file comes in, or that original set of data come in, we start to think about potentially changing the shape of the data. And that shape, oftentimes we like things square. Might not be square to start, might be rectangular, it might be inverted, all kinds of fun things. Sometimes it's squares within squares within squares. State wage data tends to look like that, with an identifier, a quarter, multiple jobs within quarter, wages earned at each job, and so forth. So we're talking about restructuring and changing the shape of the data. Typically that starts off with things like rows or columns, either adding new rows, removing administrative rows or system rows, removing blank columns if they're there, adding new columns if we need them. Headers or variable labels, some files don't come with any, some come with a massive amount of information in the headers. So we might change those in terms of changing variable names or column names. Some data systems come with identifiers, some don't. So we might create identifiers, changing row identities at that point. Next big piece is changing the actual elements in the data. And in this case, we're talking about adding or altering any value that's there. That could be a single data point, it could be a series of points, it could be entries across part of the data. But the key is that once those data are changed, any alteration of that source data, you want to do something to document what you've changed. And that documentation should be rather extensive, particularly if there's going to be a historical or archival keeping of the data. But even within a single project that might be relatively short term, you want documentation to the point of clarity that it's replicable and that could be shared back. So document everything. Spend a lot of time doing that. So when we talk about data structures, there are many different types, but I kind of classify them for myself into three major systems. One is the typical data structure that I think most people would envision, where it's a single record system. There is one row of data with one identifier for each unique observation. Data that typically should have this form would include things like birth and death records, where you shouldn't have an individual show up twice in either of those files. If they do, there's potentially something wrong. Longitudinal record systems are similar in that there is usually a single identifier for people, but they can have multiple records. And longitudinal generally implies over time, but sometimes that time is a very short period, sometimes it's a very long period. So if we think about things like educational records, we're likely to get data over time every year, but some districts, some state agencies keep that data at the quarter level. Others will keep it at the semester level. Census data, typically over years, not always. There are some things that are updated in more time than that. But generally, even if it's a system where they're keeping records on visitations, so medical records, you typically would have one identifier in that system, but you might come in 2 days in a row, producing multiple records for you. The third system is a multiple record system where there are multiple rows or records for an individual, but that individual also has multiple identifiers. Where I deal with this the most is in a lot of programs where they conduct home visits, in some preschool type programs. They don't assign a static ID to an individual. The individual is just tagged every time they're contacted. And so those types of files present some specific challenges down the road that we'll talk about. Another type of data that might show this is billing records, where you show up multiple times under an invoice, but you don't necessarily have a buyer's ID. You're just following an invoice number. And then, of course, within any particular data structure, these three systems could be co-occurring to some degree. Complication is always possible. So in terms of talking about restructuring these types of files, there's a number of things we can do. Sometimes it makes things easier to work with data one way or another. Sometimes the data system itself requires restructuring to be useful. Other times the end goal is what drives how you're going to structure or shape the data. One common restructuring approach is to aggregate data. And this is not aggregating an observation, but actually aggregating multiple files over time usually. This is an example of some fake student data where you might get a file for the school year 2015, another file for the year 2016, and so forth. And what you may actually want, rather than all of these separate files, is a single aggregated or conglomerated file that lists every individual. And so generally when we talk about aggregating the structure of the data, you think about stacking things up vertically, creating a single file for multiple files that are generally the same over time. Some other structures that are possible involving multiple files are when you want to connect them horizontally, merging files, and it's sometimes more often now called joining files, where you get multiple records that may be over time, they may be over source at the same time, different sources. And the key is that you want to line up rows in one file with rows in the other file. In order to do this, you need some sort of unique identifier per row in each file to match on. And that's where things get really fun with how people record data, how systems record data, and how much effort you have to put into cleaning data. We had a running joke here in Iowa a couple weeks ago, and this is apparently an issue that has bugged just about everybody who works in this state at one point or another with administrative or county data. Iowa has 3 counties, O'Brien, and O'Brien. And they are all the same county, but every particular data system that I've been involved with decides how they want to spell that. Sometimes they change their minds. So in one of our system files, it's O'Brien, like on the left with just a single string of text. And then for 2 years, they changed it to O''Brian, like on the right. And then they went back. And so clearly in these cases, if you're trying to do some sort of matching or linkage between 2 sets of data, those have to be unique, and comparable. So oftentimes there's, do you standardize it? Do you just create something else? One option in this particular case would be something like a FIPS code for the county level, which shouldn't change over time, even though people might decide to spell the county name different. In these cases where there is some potential overlap or you're going to join, you need that unique identifier. I mentioned I do deal a lot with home visiting types of data where they do not use a unique identifier. So some example data, you can clearly see that you have the same individual being tagged multiple times with a different data system ID. Those IDs would not be comparable across 2, 3, 4, or 5 files. So in the columns on the right, there's a count of how many times somebody shows up in a particular data set. And you can see that on the very right column, created a new person identifier that is now unique. There is one person, ID 1, that is Alice, one person that is unique, ID 2, and that's Doug, and so forth. That would then become a unique identifier with which we could join files across different instances of data. When you join or merge data, there's a couple of ways you can go about doing it. Again, depending on your goal, what you actually need the data to do right now, what you might need to do in an intermediary step, or what you might be planning to do at the end of the data manipulation process when you get down to actually analyzing. One type of joining is what's called a left join, sometimes called a left outer join. And what you're doing here is you're taking two files, file 1 and file 2, and you're matching them on that unique identifier. So in this case, student ID. And your left join then is going to take all of the rows in the first file and essentially pair them with whatever is available that matches in the second file. And you'll see on the right there that your left joined file returns everybody who was in file 1, but only those cases that matched out of file 2. So if you notice, all of the 1,700 or 170,000 IDs in file 2 down at the bottom don't get carried over. The reverse of this is a right join, where it's same two data sets are being joined. And here, the right join takes everybody that's in file 2 and carries them over, and then only brings over data from the first file where there was a match. So we lose some of the folks in file 1 that weren't repeated in file 2. Third join is an inner join, and this is what I think a lot of people would think about in terms of joining data, where you have the same two files, file 1 and file 2. And what you get from the inner join then is only the cases that are reflected in both data sets. And so this would be your, in terms of school data, would be your cohort that was in the data both school years 2015 and 16. And the last major type of join then is a full join or a full outer join. And this is the case where you take everybody in the data sets and they're carried over to a new data set, whether they're available in one file, the second file, or as you can see, in both files. Again, only the people that were in the inner join would have data in both school year columns, but we don't lose anybody who was not matched from file 1 to anybody in file 2. Some other things that we do typically with data is we reshape them from a long format or a wide format. And so stretching files, we might take a data set that comes through, like the one on the left, where you can see that there are repeats in there. So if you go down about the 4th, 5th row, you can see that ID 165,736 occurs twice. And if you go down a little bit further, you can see 168,800 occurs twice. And so there are repeats in these data. This is typically the way a lot of administrative data comes. This is definitely the way educational records come. It's very rare to get them to split people out for you. They just stack everybody on top of each other. So that may not be what we necessarily want in terms of dealing with the data. whether we're cleaning, continuing to restructure, transform, might be easier to stretch the data out to what's called a wide format. And so on the right side, you can see that that same long data set has now just been reduced to the number of unique rows under ID, but each person that occurred multiple times now has data in columns for both first year and second year. Whereas the folks that are only in file 1 that don't show up in file 2 are blank in year 2, and vice versa for the people who were new in file 2. The reverse of that then is taking a file that might come to you in wide format and wanting to structure it longwise. And this is a lot of times when I've worked in social science departments, this is usually something people would, why would you want to do this? We typically want the data in wide format. Well, again, I spend a lot of my time cleaning data, and it's much easier to look at a single column of school years or a single column of grades than it is to look at 6 or 7 school years over time. So sometimes there's just an efficiency reason to restructure data. In this case, we're going in the reverse that we just did with stretching the file, where we're going from that wide format and we're returning back to our long format, where you can again then see the IDs are duplicated to some extent in the files. So I've noticed a couple of chats. I'll try and pause periodically. I don't know if there's questions for me. Somebody messaged that it could have been worse. There could be a 4th O'Brien. I think I've seen it. So yeah, typos happen too. Fun times. So stacking files is basically just reverting a wide file back to long. Move on. There we go. Some other types of restructuring data sets don't necessarily involve altering the shape of the data, but they alter the content of the data. So we think about structuring data through what's called essentially transformation processes. There's a number of reasons to conduct transformations. One, I do, data management. Transform things so that the cleaning process is easier, more efficient, more accurate, and documented. Standardization is a big problem. Notoriously, systems will change things. I think there was a discussion on gender and race the other day about how those codes get larger, smaller, changed. That happens throughout data systems. So a particular system might change how they're coding things from year to year. So that standardization process, creating consistency across the data system. And then of course, you always have to keep in mind that there are goals of playing with the data. There are some things that you might need to compute for the analyst who's going to be working with the data if it's not you. There could be specific questions the project's attempting to answer that require manipulation of the actual values in the data to get at that question. So there's a number of common transformations. There are many, but if you think in big groups of types of transformations, missing data, there's typically something you need to do with missing data. Oftentimes people will delete it, and in some cases that makes perfect sense. As I said, I spent a lot of time doing record linkage work, which we'll talk about tomorrow. If I have a data system where I'm missing identifier information, like people's names, their birth dates, there's not much I can do with them. So I would transform those data by potentially removing those cases. Another related issue to missing data is filling it in. Is there a reason it's missing that's obvious? So typically this shows up with things like screener questions, where there is no data available for the number of alcoholic drinks somebody's had in the last 6 months because they don't drink. In that case, you might consider filling those in with zeros. It's really a sticky question when you talk about starting with filling in data. There are both ethical and legal ramifications for doing so. And then logically, you have to make sure that you are not altering or systematically biasing what you're going to be working with. Second type of common transformation is recoding data. And this is a case where you're again working to either correct something that's changed. You're not altering the data, the spirit of the data. You're altering how the data is represented in a file over time or across systems. This falls back on things like standardization. Different systems might index gender 5 different ways. They might use a number, they might use a letter, they might use a word. We want that standardized across files usually when we're working with data so that we can simply combine columns, combine information, and not have to deal with 4 or 5 different values for the same category or group. The third big type of transformation that alters data is indicator creation. And indicator creation is most often driven by whatever the analytic use for the data is going to be. It's not necessarily the case that the raw data you have are going to do any good for people who want to, it would be the end users of the data who are trying to answer specific questions. So often we'll combine elements in a data set to create something new. We might take differences between test scores over time. We might create percentages out of variables. So indicator creation is, like I said, most often driven by analytic goals. But there are also some reasons on the data management and cleaning side to create new indicators if they help you identify systematic biases, problems in the data that are specifically relegated to certain subgroups. So indicator creation can be a valuable data cleaning tool. The last type of transformation that alters the nature of the data, but not necessarily its actual structure, is subsetting. So oftentimes we may have a broad question to answer that really only focuses on a piece of the data that we're collecting or that we have. Oftentimes this is a case where we might follow a particular cohort over time of kids, or we might be looking at only people born between certain time periods. We might only be looking for people who participated in home visiting programs in a 6-month period. So in that case, we're not changing the nature of the data or the structure of the data, but we're removing people, and we're removing people for a dedicated reason. So these are the general approaches to restructuring data and transforming data. And it was at this point that we were going to try and jump on R and do some restructuring. It's kind of like that. So if you are able to access the file and the data, we can follow along. If you aren't able to, or you don't have R installed locally, you kind of sit back and watch what we're doing. I'll talk our way through it. Most of this, I think, is going to work fine in base. You will need to load data table as a library, going only for reading purposes at this point. And then the 3 data sets that we're going to be using are just CSV files that are also in that same location in the repository. Don't set your working directory to my computer. And so what these data are, real quick, is they're completely simulated fake data. I intended them to mimic sort of educational record data. Everything I deal with, real data-wise, is locked in a room that I can't share with anybody. So I generated these the best I could. If you see anything odd or unusual, like a particular child going backwards in time from 2nd grade to kindergarten, just gloss over that. It was late last night when I got these done. They are 100% fake, so I'm glad we're not doing any analyses, but we want to load all 3 of these. And the files themselves are like the first set I showed you when we were talking about stacking files. Basically, there is a file from 2015 that has kids in it ranging from kindergarten to 2nd grade. There's a file from 2016 and a file from 2017. And so when you load those, you'll probably quickly notice that what should happen with education data is that the files change size over time, which is important. As we move from 2015 to 2016, most kids should move ahead in grades. Some kids disappear, they leave the district or they leave the state. New kids enroll in school, they move in. Obviously, there's always a new cohort of kindergartners starting. So each of these files is a different size. It does not mean that each of the files contains the exact same sets of people. So typically, these are the types of data I get. And one of the first things I like to do when I receive data from the same system is to verify that they are at least containing the same sorts of things. Yeah, if Chris's suggestion will work, download them and just read them in. They're not very big files, so that is going to be pretty quick for you if it's taking a while to clone the repository. Yep, Jesse, if that works. Like I said, they're not very big files. They're 1,000 records, 1,500 records, and I think 5-6 columns, something like that. So one of the first things I like to do is I like to see what's in them. Oftentimes I will actually just visually look at them. But one of the first things that I've repeatedly run into is that what is in the files necessarily shouldn't change over time if they're from the same system, but they do. And so just examining column names in the 3 files, again, things should be reasonably consistent, right? There should be the same columns or elements over time. Not always, sometimes that changes, particularly if a system starts collecting new information or discontinues collecting old information. Columns will appear and disappear across files across time. In these particular files, they're all about the same length, right? They all have 10 columns, but quickly might notice that they're not all the same in terms of what's there and particularly what order things are in. Key pieces standing out being the free or reduced lunch column that's in 7, and that then lines up with a different spelling of what is hopefully the same variable, and then that lines up with a column called math. So at this point, and again, this is a simple example. If there were 100 variables in each file, this would be a mess to try and read through. Try to do some things to compare what is in each of the files with what's in each of the others. So one quick and easy way to do this is something called a set difference. The set difference is just that. It takes whatever arguments you're giving it and determines what is in both and not in both, but it works one directional. So the way that first one is written, it's going to look for elements in the first file that are not in the second file. It doesn't do the reverse automatically. And so here, we're actually set to look at only the column names, not looking at the actual data themselves, but just the column names and which names might differ between 2015 and 2016. So click run. And it tells us that that FRL, free reduced lunch variable in column 20 in the 2015 file is not in the 2016 file. So I say it works one directional. So if you're going to do this and use this approach, again, more useful for small files, you flip them around and now have it look for everything in 2016 that's not in 2015, and that will give us the other version of free and reduced lunch. When files are small, this works pretty well. It's quick, it's easy, but you do have to do that in both directions. With bigger files, it might take something along these lines, which looks like I stepped, yeah. So I'm using the same thing. I'm using that set difference operator again, but here I'm combining it with a union command and an intersection command to get, so the union command is going to take everything in 2015 and 16, every column name, and then the intersection is going to take only those that are common And the union is going to then subtract out the common, which should leave me the entire set of column names that are unique across the files. To do that, we get both of those two variables. This works pretty well. It's pretty quick. This is much more efficient in terms of files that might have 50 or 60 columns each. And it will pick up things like spelling, different names, actual truly different columns. And then the downside is that you do this comparison across all the files that you're going to systematize. Now, scroll just a little bit back up. FRL in the 2017 file and FRL in the 2015 file are consistent. So the rest of the variables there, curious about whether or not there are other differences. We're not concerned about that one. But if we run this, we get an empty set back. Importantly, that empty set is telling us that there are no column names in 2015 that are not also in 2017 and vice versa. But note that it doesn't tell us anything about the ordering of the columns. So if we look at that, we notice that in the 2017 file, the math variable is the last one, but in the 2017 file, the attendance variable or days attended is the last one. So the column names are the same, they're just in different orders across the 2015 and 2017 files. First thing we want to do in terms of standardization, and hopefully we have a way of verifying this, that FRL and F period R period lunch are in fact both indicators of free and reduced lunch. If they are, we want to standardize them just so that we have a consistent column name moving forward. So just using a column names command and a location, the 7th column, and I'm going to go ahead and pass the name from 2015 to the file in 2016. We can do that from 2017 backwards, or we could actually just enter the text here as a text indicator. But that will then standardize our FRL column across the 3 years. Now we're ready to start working with the structure of the data. First thing we want to do is that first example of stacking these up, aggregating them up. And what we're going to do then is bind rows in the files. There's a number of different ways to do this. I've got an example here. Be cautious though. In this particular example, I'm using rbind list. There's also another way of doing this is just rbind. Rbind is smart, where it will automatically line up columns when it adds them together, stacks them. Rbind list, the default is to use location. So it would line up column 10 and column 10, regardless of what's in those columns. And if you make that mistake, then obviously we're going to have a 10th column that is full of math scores and days attended. In this case, those could be very similar numbers, but we'll also end up with some very strange things back here. Math scores lining up with a yes and no variable for free lunch. So be cautious about the defaults. In this case, because rbind list uses location, I'm actually tagging on and asking it to use the names of the columns. Again, something like rbind, this wouldn't be necessary. But if we do that, click run, and take a look at the data that we've now created. So we've created a new data set called schools data that has just stacked these 3 files on top of each other. And it's just a head command asking for the first couple rows in that data set. So we can now see that everybody's piled on top of each other at this point. And all the column headings are unique or consolidated, so FRL is fine. And again, if we took a tail command or a sample command of these data, we would verify that we didn't misalign anything, but we're good here. So we've now actually created that first type of restructuring. And if I was going to do some data cleaning with these files, this is probably the first thing I would do. Again, because if I was going to go through here and change ELL to some other value or do something with these variables, I wouldn't want to have to do that twice, 3 times, 4 times, however many years I have. I'd rather just recode or change ELL once. And then if I need the data strung back out, we already know that we can go from long to wide. That makes sense. Any questions? Everybody good? Don't see anything popping up in the chat. Okay. We might also then want to create a wide file. So we might think about joining these files. We'll walk through each type of join, and we'll see something similar to what I showed in the lecture slides. The first place we're going to start is with just a simple left join. And we're going to keep all of the records in the 2015 file, but we only want to retain the matches in 2016. This would be a situation where you're trying to follow a particular cohort over time. You may not want the noise of new kids coming into the class or into the school system. You are interested in the ones that disappear. So if there's a record in 2015 and that child moves out of the district or out of the state, they won't have data in 2016, but we want to retain their records so that we know they've left the system. And so that's just a left join. Again, many ways to do this, but here I'm just using a base merge function where I define the X and Y side of the tables that I want to join, what the unique identifier is, and this command at the end, all.x, that's telling it to keep everything in the X side. So a left join in this case. Run that. And then here is just a command to look at missing IDs on the Y side, just to see what the data actually look like. If we do that, what we'll note is that everything on the X side in 2015 is there. Some of them are not in the file in 2016. So this is our left join. And again, if you went down through the file, you would also find that there were people who were matched that are there in 2015 and 16. The key is that we have not lost these data points back in 2015. We just now don't have data for them moving forward. Once you've done a merge, it's default for it to assign some periodicity indicator. Here it's using X and Y. Sometimes you'll see 1s and 2s, vice versa, all sorts of things. Easy enough to clean up. Just use a paste function to add the correct year to the names. And so if we do that and then take a look, we'll see that we now have these nice pretty names of what school ID was or what school they were in 2015. Again, they can change if there's data for them. Their school ID could certainly stay the same or change. If this goes over a long enough period of time, students will absolutely change schools as they transition from elementary to junior high to high school. And so we may want to know those things. Obviously, their grades will change and so forth. So our left join might also then want to consider a right join. And this would be a case where we keep all records in 2016 and the matches from 2015. So this could be a case where we're actually looking at the cohort of kids who were in school in 2016, and we want to know whether or not they have historical data. We want to see if there were things in the year prior that are related to or predict things in the current school year. So there, our focus is going to be only on maintaining those 2016 kids, but we'd want anything that we could get from 2015. So a right join, it's the same merge command, but here I've just told it to keep everything on the Y side, so from file 2. And if we do that, and take a look at that file, we can now see that we have people who are here in 2016 that did not have data in 2015. And of course, in the file, there are people who are matched 2015 and 16. We can clean up those column names again, doing the same thing. You don't need to run it again if you don't want to, but again, tag on nice column names. If our interest was actually in following a cohort of kids who we have data from in both years, then we would be talking about conducting an inner join. That's where we would want to keep everybody in the 2015 school year who also has data in the 2016 school year. And so that inner join, again, same merge command, but notice that there's no keep X or keep Y out here. The default is to only keep matches in both files. So our inner join is pretty simplistic. We run that. And then this is just a check. There shouldn't be anybody with a missing ID in either year. This was an inner join, so everybody who is in 2015 that matched somebody in 2016 are the only people that should be in the file. And so our request to show us any missing IDs correctly results in an empty table. That's a good thing. We clean those up again and take a look. And now we can see that we've got what is essentially full data, complete data. Right? Everybody in 2015 that also had data in 2016. Last join we'll take a look at is the full join. And here we're going to keep everybody in 2015 and everybody in 2016, whether they have data in both years or not. So here we got the merge statement again, and now we just add both commands to keep all X and all Y. So we do that. And then our check is going to look for anybody that is missing an ID in either year. And here we should have people that miss an ID in one year or the other. And we do. So here are some folks that have an ID in 2015 that do not have data in 2016. And if I got lucky, we went backwards too. These folks down here have data in 2016, but not in 2015. And of course, the folks that have data in both are in there as well. So we clean up the columns here again. And then this is just a check taking a sample, a random sample of these cases, 20 of them. Basically like a head command again. But now we can see kind of a more full picture of the data where our folks who have data in 2015 might have data in 2016, might not have data in 2016, and vice versa. People that don't have data in 2016 could have 15 or not have 15 data. So this keeps everybody in the final file, whether they have a match or not. Our last step here then might be to match the full 2015, 16, 17 cohort. And this would be somebody who's interested in following those initial kids in 2015 through 2016 and 2017, so 2 years of school. And here the interest again would be an inner join. We want to keep everybody who has a match in 2015 and 16, and then add in everybody who matches in 2017. We've already conducted that first inner join with 15 and 16. So if we use that again, we change the data set here, here. We're creating this 15, 16, 17 sample. We're again conducting an inner merge, so we're just bringing in the new 2017 file. We don't need to keep all X or all Y. We just want the full matched set. We run that. And then we want to clean up the columns again, just so that the headings are nice and yearly dated. But remember that we've already done this for the schoolid.x, schoolid.y part. So we only need to clean up the column names for the new variables in 2017. So we're just adding those last 9 columns and tacking them with 2017 as the year. And we can take a look at those data and notice that this would be everybody that has data in 2015. So there they are in 2015, data in 2016, right there, and data in 2017. And obviously we could do this again as an outer or full join. What we would potentially end up with there is cases, we'd end up with these cases that have data across all 3 years. We'd have a group of people who had data in 2015 and 16, but not 17. We might end up with a group of people who have data in 2015 and 17, but not 16. Kids who move out of district in 1 year and return the next year. And all possible combinations, in addition to people who are brand new in 2017 and have no prior data. Again, it just depends on what the end goal of the data restructuring and analysis is in terms of driving which way you alter or reformat the data. Any questions on joining? Everybody feel good? Okay. So stretching files. This is that long to wide format that we discussed. And we could, if we think about how schools are actually sending data, I mentioned that they most often send educational records in that long format, where each kid is there, has a row for every school year. Even more potentially complex is when they collect data on a more expedient interval. So if they collect data on quarters or semesters, within each year, each kid could have multiple rows of data. Test scores work this way if they're administered multiple times over a year. In Iowa, they actually have assessments that are completed 3 times a year for elementary school kids. So those data will come with the kid, the semester, spring, winter, fall, and then how many times they completed a test in those quarters or semesters. So that data set is usually a little messy in terms of trying to figure out what's happening with test scores. That long file we might want to restructure into a wide file so that we can see things over time horizontally. And so first thing we're going to do is take that long file that we have and sort it. This is kind of just a thing I like to do. It's not necessarily mandatory that you do this, but it's helpful. And I'm just going to sort by their school ID and, or sorry, the student ID and the year that they're in. And so that's that first long file we had. And one thing I like to do when I get long files or I'm working with them, it's again, not necessary to do this, but it's helpful down the road, depending on what you're going to be doing with the data, is I like to create counters of people or records, observations, whatever the data happen to be, so that if I wanted to go in and to this long file and determine who I want to pull out that would have data in all 3 years, I could just simply select them out if they have a 3 on this new counter. Alternatively, if I was interested in people who didn't meet the full 3 years, I would take everybody who has a 1 and a 2 on this counter. Again, not necessary to do this, but it can be very helpful in terms of shortcutting some things you might have to do later. And so all this is going to do is just create a count, N, by student ID. How many times does it appear in the file? And then the next thing is just going to generate a simple table to show us how many times we see 1s, 2s, and 3s. Okay. This is not necessarily the total set that you'd be interested in, but if you were interested in the inner join, so to speak, it's these 2,400 lines that appear, the ID appears 3 times for them. But remember that they're long. So there's 3 records for each person. If we divided that by 3, we should get back to the same sample size as our full 3-year join. Second thing I like to do, again, worked a lot with longitudinal type data. You typically want to know when things occur. So this is slightly different. I'm creating an observation counter. Again, optional, not that you have to do this. But here what I'm going to have it do is go through and count when each one of these multiple IDs occurs. And so if we do that and then look at a simple table of that, we see slightly different numbers of when, of the 1s, 2s, and 3s. And the easiest way to sort of see what these two things are doing differently is to cross-tabulate them. Let's see like this. We'll notice that everybody who has a 3, that means they're there every year, they have an observation at time 1, time 2, and time 3. The people who only have a 1 don't have observations later. The people who have a 2 only have observations at times 1 and 2. Again, optional things to create, simple things to create that can become really handy later. So now to get to the actual reshaping, we want to create a wide file. We're just going to use the reshape routine to do this. We feed it a data set, so we're going to use this schools long. The time variable here is school year. That's what differs over each observation, right? 2015, 16, 17. ID variable is a misnomer, so to speak. It's the ID you want to break on, but it's also a place where you put variables that don't change over time. So sometimes you'll hear things like fixed variables or time invariant variables. This observation counter that I made does change. If somebody's in the data set 3 times, they have a 1, 2, and a 3. But the frequency counter is a 3 at each time. They're there 3 times regardless of which row of data you're looking at. So that variable doesn't change over time. And so it can go in there as a fixed variable. And the last step then is just telling it we want to take this data and turn it in the wide direction. Run that. And then I'm just going to draw a sample of 10 cases so we can take a look at how this turned out for us. And if we go up to the top, we have an ID. That person only was in the data set 1 time. And so what you'll notice is they have no data in 2015. They have data in 2016. And they have no data in 2017. So we know they're in there 1 time, but it's that observation counter that tells us where they show up. So if we look at that row again, that first row, in 2016, that's the first time they were observed in the data set. They could have been observed at 2015. They could have been observed at 2017, but now we know. And so if we were interested in only the kids who are brand new in 2016, I can run back in and just grab all the ones who have a 1 there. The same thing if we were interested in kids who were brand new in 2017 or only the subsample that was here in 2015 and 16. Easy enough to select them out based on these new counter IDs. Any questions about stretching data sets to wide format? So then the reverse of that, stacking the file back to a long format, we'll take this wide file we just created. Doesn't have to be the one you just created, but it's the easiest one available. So we'll go ahead and just flip it back to the long structure we had. I'm going to use that reshape command again, feed it the data set. And here the ID variable is ID. That's the one we want it to break them on, pushing them into rows now from columns. It's going to take every element of their columns and move it. We have to tell it what elements need to be moved. So this varying command, these are all column assignments. A recommendation in your own work when you're doing this, and I simply forgot to do it last night, reorder everything so that the same columns are like 1, 2, 3, then 4, 5, 6, or some system 1, 9, 18. I forgot to do that. So in my file that was off initially in the 2017 file, I had to go back through and recount where all these were. But that's what we're doing. We're saying we're going to create a new column in this long file that will stack everything in column 2, 11, and 20 of the wide file. In vnames, we're naming what that new column will be. So this is going to be their school ID. The same way here, we're going to take everything in columns 3, 12, and 21, and that's going to be the new year variable, grade, so forth, enrollment, attendance, all these variables. And then we're going to finally tell it the direction is long. We'll go ahead and run that. And then if we go and take a look at this, we'll see that the data has now popped back to this long format. And if we go up, it creates a nice time variable for us. So it's telling us when their observations occur. If we just take a quick look at time itself, we'll now see that there are 816 observations at each time point, because we started with our source file of the inner unit or the inner join. Does it make sense? Everybody happy with restructuring? Okay. Let's talk a little bit about transforms. And again, we're not going to go through the litany of possible transformations, but just some general ideas of things that might be done that are common to do, and also some things that are tied to restructuring that might be useful. So again, we talked about missing data, dealing with it. We know we have missing data, even in any one of those given files in 2015, 16, or 17. There are some kids that don't show up on the days they administer tests. So they have a missing value. Usually there aren't missing data in things like year, grade, so forth. But when you get into indicators of other things, like free lunch status, free reduced lunch status, there could be missing data, other types of things like that. And so if you're working with the data, in this case, that requires having those test scores, there's no reason to keep all of the elements that don't have them. So if somebody's only interested in analyzing cases where there is a test score for both reading and math, then we can go ahead and eliminate those that don't have test scores. And so we're just going to go ahead and sub the file, take a look first at how many cases that might be. So it's whether or not they're missing a reading score or a math score. And this is again the full sample that we just created. And so we're starting out with a sample of 816 cases that are interjoined from 2015, 16, and 17. Of that 816, 178 are missing either a math score or a reading score or both. So we might decide we're going to go ahead and eliminate them. We'll just subset them out. And so now we are in a sub file. Always a good idea to follow that naming convention. Anytime you make a change, create a new file. And so we're obviously going to now have fewer cases. Next step we might consider is converting text entries or codes. This is usually an analytic decision. Sometimes people will leave those as factors. So ELL is coded as a yes or no variable in this case. Sometimes people will leave that as a factor that can be treated as yes, no if you're going to look for like group differences across that, or if you want that for plotting purposes. In other cases, variables like that are converted to numeric values for a particular reason. Typically in the social sciences, we like to use numeric codes for grouping variables if we can. In terms of an analysis goal, if you're trying to relate variables to the probability of a student being in an ELL program, you might want to have a numeric variable that's coded 0, 1 there for the ability to use that as an outcome in a particular statistical model. So recoding, there's a number of ways to do this as well. I'm doing something very simplistic here. And I have a warning to myself and to you. This works because there are no missing values in this data set. There's 816 complete cases. But what we're doing here is just using an if-else command. So if this variable equals the original variable equals y, set it to 1, everything else is a 0, which is the end goal I'm trying to get to. But keep in mind that if there were missing data here, this would be a bad thing to do. And this would then code everybody who's missing as also a 0. So we wouldn't want to necessarily do that. In addition to just converting that over to a 1 and a 0, it's already a character string. So I'm also requesting that the result be returned as an actual integer number. So do that. So now I have a variable that could be used as a factor or as an actual outcome, a numeric outcome in a modeling application. The next piece to talk about is counting cases. This is, again, gets into sort of subsetting, things like that, where what I want to do here is go through and count how many cases have, or for each case, how many of them are in an ELL program or are eligible for free or reduced lunch status. Just checking the chat. Yes, feel free to offer suggestions to other folks about other ways to do this. There are tons of ways to do things, and I just went with the ones that made sense to me at the time. So what we're going to do here is actually try to count the number of ones that occur over these two columns. In this case, it's pretty straightforward. We know we're going to end up with zeros, ones, and twos. But if we think about this in terms of a much wider set of opportunities, so let's say 30 columns could reflect birth risks or something that we work with quite a bit. We want to count up how many are occurring. This doesn't necessarily tell us where they're occurring, but it will give us a count. And so what we're going to do is have it go through and sum the rows and then bind those back as a column. And you'll notice right down here I have it annotated out, but if I had just added the two variables together, free and reduced lunch plus ELL, I would have ended up with a column of zeros, ones, and twos. There's a reason why I didn't do that though. I'll show you here as we go down. So then next possible sets of combinations of things we might do would be statistical summaries. You might want to average test scores, math, reading scores over years. You know, kids can have bad days when they test. Maybe you get a better picture of their math and reading proficiency by looking at the cumulative record. We might do this particularly more so in the case if they're taking multiple tests within a semester or multiple tests within the school year. We might be looking at their year average versus their performance on any given day when the tests were administered. So in this case, one thing we could consider normally is that we could just add their 3 math scores together and divide by 3. That would give us an average. This is where structure and restructure and formatting and transforming can come into play in a combination. Our data are in long form here. So if we were just, there is no math 15, 16, and 17. There's just math. That's all we have. And so what we really want to do is average those 3 numbers within ID. And so these commands are just going to average along the math variable for IDs that are the same. So here's our function mean out here. And I'm doing one for math and one for reading. Get a little bit more complicated with what we're trying to compute. Mathematical transformations. So attendance is a huge one. It's related to a lot of things, including performance on exams, behavioral problems, all kinds of fun stuff. And we know that kids that don't go to school enough tend to fall behind. So we're always interested in attendance. But looking at the number of days attended is often misleading, particularly if you're dealing with a population that is mobile. Students might enroll for 30 days at a school and then move across town and enroll in a new school for 100 days. So what we're really typically trying to do is come up with an index or an indicator that is scale free from that is not contaminated by how many days they're actually enrolled. And so simplest way to do that is a percentage of attendance to enrollment. So we're going to create this new variable, a 10%, where we just take the number of days they attended divided by the number of days they were officially enrolled in a school and multiply that by 100. It's in a percentage form. And then the last sort of transformations that we talked about were subsets. Subsets are usually what folks are after. They want particular groups of people. Remember, we've started doing these transformations in a subset of the original data already. We're only dealing with the kids who are in the data set in all 3 years. So 2015, 16, and 17. We've now created a number of variables and recoded some variables for use in analyses. And now we might want to focus back on the problem at hand, the goal of the data, what questions we're trying to solve. Might be interested only in kids that are falling below proficiency cutoffs, and particularly if they're below the proficiency cutoff at second grade. So we can subset them out. Math and reading proficiency scores less than 182 and 190 respectively would be below cutoff. So we want those kids out. But we also then said those are the cutoffs at second grade. So we want to make sure that we limit only to grade 2 data. And remember, in this case, everybody has grade 2 data. So if we create a new data set, come up with your own nice naming conventions. Mine is the original file, second grade, not proficient. Keep records of those. 6 months later, I'll have no idea what that means. We'll click run, and now we've got a new data set. And my little chat window is over, but if you look over in your data environment, you'll see that our new data set long is reducing substantially. Let's see if I move that up. No. Oh, good God. There we go. So now we're down to 267 cases. Is that right? Here. Yep. So then we might also subset further. We might also want to then know of that group, how many of them, or let's limit analyses where we want to take a closer look or focus on those who have risk factors. So free and reduced lunch status, ELL enrollment, both related to test scores for obvious reasons. So we might be interested only in those kids who are below proficiency in second grade, where that new count of free reduced lunch and ELL is 1 or 2. And so we could do that in a couple of different ways. We could go back to the original file, long 15, 16, 17, take out the second graders who are not proficient, who are also at risk. Just add something else to the subset command. Of course, we could also subset this file that we created to only keep the folks who have a risk score of 1 or 2. Take them out. And now we notice our file, new file, and we're down to 146 cases. This might be the final analysis sample that somebody's interested in using. So this is what you might provide. Alternatively, if you're the analysis, this might be where you now switch over to analyzing the data. And we have these nice indicators built in. We have all these great composite or total scores, percentages, averages, all this nice stuff. I generated these data randomly. So if you do any analyses, don't be surprised that nothing is related to anything. I was hoping to show you a neat scatter plot, but no, nothing's related to anything in these data, which is unfortunate, but didn't build in any structure. So any questions on restructuring, formatting, transformations? The end of my R demonstration. For those of you who were able to follow along, fantastic. If there were folks that could not, feel free to take those files and run through them at your own time. A nice opportunity for those of you who particularly might focus more on writing in tidy is just take that script and write the tidy code to generate the same results. I'm sure you'll come up with probably faster and better ways to do it. If you find something that you did find a faster and better way to do it, let me know. I'll use it. Otherwise, there's no questions. That ends my restructuring and transforming story. Everybody good? Don't see anything. Oh, there's chat. All right. So tomorrow, I believe, I'm not going to jump into data cleaning right now. That it's way too involved. But tomorrow we should pick up with data cleaning. I believe after some rescheduling, we'll do data cleaning and then immediately follow that up with deduplication and record linkage, which is where all of this restructuring stuff is going. So